European Space Agency for supporting me here. Well, my name is Emilio Mondragón IAC. I'm a fifth-year student at the National Autonomous University of Mexico. Right now, this is the design and development of an aerospace power system. This is being developed at the Laboratory of Electronic Instrumentation for Space Systems, and these are the early steps for a thesis of the Bachelor degree. So, this is the general concept, since it's still in early stages, so we still have no actual development. So, as we all know, aerospatial technology is one of the most demanding and expensive sectors of engineering. Starting with the International Space Station, this currently exceeds the cost of $150 million. So for a long time, everything related to aerospace technology was only available for very few companies, very few people, especially very few countries. So with the introduction of the CubeSat platform back in '99 by the California Polytechnic State University and the Stanford University, projects like mine are possible. So we based our whole design in a 3U platform. Thankfully, we have a growing community of universities and non-profit organizations, and thanks to all of this documentation, I've been able to develop and understand a little bit more for the thesis. Currently, CubeSat is expected to cost around $100,000 US, and earlier this year there was the record of over 150 successful missions. Currently in the laboratory we're developing three different missions. The first of them is our remote sensing system. This is based on an FPGA-based design with a 5-megapixel camera, so we'll be able to obtain and transfer high-definition images back to our ground station. Then we have an onboard machine vision system. This is thought to be this will be applied to a microgravity experiment. And finally, we have a software-defined radio. This is one of the early stages for approach to a more versatile communication system. So we have three different missions. Each of them have different demands for energy, and each of them has they all start with the same beginning of life, and we have the end of life. So we expect for all three missions to get to the end of life eventfully, and if they do, then we'll consider them to be a successful mission. Well, the truth is, not all of our three missions have the same end of life. So what we'll be doing, first I was tasked with finding a commercial solution for the electronic power system to apply to our systems, but there was a big gap in the difference between the different power demands of our three missions. So not the same design or not the same commercial solutions were available. So then we decided we needed to develop our own in-house electrical power system, and since the CubeSat platform is thought to be an academic tool, that's what we will be doing. So by using the same platform for all three missions, then we're going to be using the same design, and then therefore our mechanical design can be reused, and even though the final design will not be exactly replicated in each of the missions, then it will be easier for us to apply for other missions down the line in the university. So each of them has a different end of life. So we'll be taking the longest end of life for our mission. We're expecting to have close to 2 years, more or less, still to be defined. And we're gonna, for our design parameters, we took the highest power demands to be considered. So first, we looked at the architecture for electrical power systems. Currently, the most popular is centralized and distributed and intermediate bus. Even though traditional spacecrafts have been using a distributed power system with a single power bus, most CubeSats use a centralized power architecture. Having all power processing in a single bus does mean we have less space, because usually when in platforms such as the CubeSat, you are always restrained by size and weight. So having a centralized, when you have all in a single box, will help with having more space and less weight available for our payload. Then towards the topology, more commonly we have the direct energy transfer and the peak power tracking. Direct energy transfer, that means you have directly from the primary power source towards the payload, and you have a secondary power source. This is the most simple topology there is available, and even though it does have a lot of, it is not the best one. So we chose the peak power tracking. This is the most versatile, and this means we can build a more efficient system. The electrical power system should, well, the objective is the generation, control, storage, and distribution. With our topology will be fulfilling all of these constraints, and we always have limitations. All of these limitations are set by the CubeSat standard of core size and weight. Considering the previous missions, we can usually the electrical power system consists of around a third of the final CubeSat weight, so we're going to our science to be under 230 grams. Then we have the power control needs to be compliant with all the load requirements, so we need to have the voltage range, current, transit time duration, and the voltage ripple. If our design power systems can provide energy that fulfills all of these requirements, then we can expect to have a mission with an eventful emission, and then all of our electric systems will be stable. Finally, we chose this topology. That is a fully regulated bus with a big power tracking system. First of all, we have a solar array, then we have the big power tracking system. We have a charge that goes towards the batteries, and boost regulator to maintain our current and voltage when we go towards the distribution and finally the load. As a primary power source, as it has become standard, we're using a photovoltaic array. We need to increase the available power, so we'll be designing a deployable array. This is going to be done by some of my colleagues, so we don't have a design yet. But there are a lot of designs that have already been used on a lot of CubeSats, so we'll probably be based on what has been developed earlier. And also the technology with solar arrays has improved a lot. So looking at single junction technology, there's an expected efficiency of less than 20%. So if we have the budget, we'll be going with the triple junction technology. We are expecting an efficiency between 25 and 30%. And earlier calculations where we don't have a final payload, so we don't have the exact power we need to be designing this for. So using a very light calculation gave us a couple of rather 8 watts, so we will have to design an 8-watt deployable array this will be able to provide for all of our 2 payloads, even though we expect actually the actual consumption to be 6.5 watts. So even though if we do this design, we may be able to downgrade a little. As a secondary power source, because we need to maintain the quality of our energy, for example, energy, we need to avoid all the eclipse zone, all the lack of stability in the eclipse zones, and during the big power demand periods, we're using batteries. So the most commonly used are both lithium-ion and lithium-ion polymer. We decided to go to the lithium-ion because of the battery cell energy density. It's higher compared to the lithium-ion polymer, and also it has it's been proven in previous missions. So we don't make a dust in that line. And then finally we have the maximum power point tracking system. For the maximum power point tracking system, we have first of all, we have a primary power source, we have a solar array. So solar arrays they're quite sensible towards temperature changes, and also a high demand current can drop our voltage. So we need since we have a non-stable power supply, we need the maximum power point tracking during the operation of our satellite. We have this graph right here that is cell current versus cell voltage. So as we operate, we need to be compliant with this a very small gap of voltage and current changes, and we want to, as we move towards different levels of irradiation and levels of temperature, we'll have different points of maximum power point. So our objective is to be always operating on this maximum power point that will guarantee us the maximum efficiency in the whole system and in the whole operation. For the maximum power point tracking system, there are a lot of algorithms available. So we made I made a small analysis of every kind of algorithm available, and we decided to go with the Participación algorithm. This has been used in earlier missions and is quite well known. And we went with this algorithm because it's very easy to apply towards a microcontroller. That will be our primary control source, and it can also be implemented with an analog circuit. So how the Participación algorithm works is that we have a change in the duty cycle, and as the duty cycle changes, we have a lecture, and then the lecture is compared to the previous lecture, and as we approach the maximum power point, then the duty cycle is changed to always be operating on the maximum power point that previously operated, so making the whole deployment and the whole operation as efficient as possible. It will be implemented on a microcontroller and an analog circuit, and well, that's pretty much the development we have so far. It's still in an very early stages, and we will hope towards the next year we'll be able to finish and to have a final